Welcome to the final video of a series of short lectures entitled The End of the Calories In, Calories Out Theory. My name is Francisco Arencibia-Albite. I am an associate professor of human physiology at the Universidad del Sagrado Corazón in San Juan, Puerto Rico. The aim of this lecture is to demonstrate that the coincidence of energy balance and weight stability is impossible. The concepts and results discussed in this lecture are original and were published in August 2022 in the Journal of Theoretical Biology, and the article is of open access. I now explain the essence of the principle of explosion. An inconsistent theory is any theory that leads to contradiction, that is, to the coexistence of incompatible outcomes. For example, being weight stable and losing weight at the same time, which, as we will see, is one of the conclusions that emerges from the calories in, calories out theory, when the framework is forced to its analytical boundaries. The principle of explosion that arises from classical logic asserts that once a theory leads to a contradiction, then any hypothesis, either true or false, can be proven. Therefore, such a theory cannot advance understanding, since the theory cannot be used to distinguish between a true or false conclusion. A historical example that illustrates the principle of explosion is Aristotle's theory of motion. In 1638, Galileo Galilei published a manuscript entitled Discourse and Mathematical Demonstration around two new sciences. In it, he used the method of reduction to the absurd, which I explain later in the lecture, to demonstrate that Aristotle's theory is in effect inconsistent. An erroneous hypothesis that emerged from Aristotle's framework was that heavy objects fall faster than light objects. Such hypothesis seems to be true as validated by a simple experiment: the simultaneous drop of a feather and a stone, where the stone hits the ground first and then the feather. Today, with modern technology, this experiment can be repeated in a vacuum to demonstrate that this hypothesis is in effect false, that is, objects of distinct masses fall at the same rate as shown in the picture. Two conclusions follow from this discussion. First, any inconsistent theory needs to be rejected, as such a theory limits understanding. And second, it is possible to collect experimental data that seems to be in perfect agreement with a false theory. To close the discussion on the principle of explosion, I would like to share a quote by the prominent American engineer Vannevar Bush, who was one of the co-founders of the National Science Foundation. The common idea that scientists reject a theory as soon as it leads to a contradiction is just not so. When they get something that works at all, they plunge ahead with it and ignore its weak spots. Scientists are just as bad as the rest of the public in following facts and being influenced by mass enthusiasm. In my opinion, this quote exemplifies what to expect when scientists are confronted with evidence that show that their working theories are inconsistent. I next explain the method of reduction to the absurd or the impossible, also known by its name in Latin, reductio ad absurdum. This antique tactic of reasoning is a vital tool in the fields of philosophy, physics, and mathematics, as it serves to enforce the consistency on emerging theories or hypotheses. The rationale of the technique is as follows. If a hypothesis that is forced to its logical consequences leads to the absurd or the impossible, then it must be false, and thus its negation must be true. Let us consider the following mathematical example that illustrates the principle. Say that someone incorrectly claims that the number 5 can be divided by 0. If this claim is true, then 5 over 0 must be equal to some unknown number x. If we can find the number x, then it is also true that x times 0 must be equal to 5. But since x times 0 is 0, we arrive at the absurd conclusion that 5 equals 0. Therefore, the negation of the claim must be true. That is, it must be true that 5 cannot be divided by 0. In this lecture, I will show that the enforcement of numerical consistency into the energy balance hypothesis leads to impossible conclusions. Therefore, it must be true that at a steady weight, the average absorbed energy intake is significantly different to the average expended energy. That is, the calories in, calories out theory must be a false paradigm. To improve the clarity of the proof that the calories in, calories out theory is a false paradigm, I first provide an overview of its logical structure. The energy balance hypothesis asserts that if the difference between the average absorbed energy intake and the average expended energy is 0 or insignificant, then body weight must remain stable. On the other hand, in Lecture 1 we define the average VO2 deviation as the difference between the average daily O2 volume uptake and the O2 volume required to oxidize the daily average absorbed macronutrient intake. This definition in turn serves to classify all cases that satisfy the energy balance hypothesis into 3 mutually exclusive categories. Type 1 energy balance, where the average VO2 deviation is negative. Type 2 energy balance, where the average VO2 deviation is 0. And type 3 energy balance, where the average VO2 deviation is positive. As we will see, the application of the analytical results obtained in lectures 2 and 4 to each one of these categories leads to the following impossible conclusions. Under type 1 energy balance, fat mass is at the same time stable and decreasing. Under type 2 energy balance, body weight is at the same time stable and decreasing. And at last, under type 3 energy balance, fat mass is at the same time stable and increasing. Altogether demonstrates, therefore, that the calories in, calories out theory is an inconsistent pattern, and as such, it must be rejected. In Lecture 2, it was demonstrated that during prolonged weight stability, fat mass remains stable as predicted by the shown equation. In Lecture 4, it was proved that, according to the calories in, calories out theory, at energy balance, the average daily fat mass change is directly proportional to the average VO2 deviation, as illustrated by the shown formula and its graph. With these facts at hand, observe that in all cases of type 1 energy balance, the average VO2 deviation is negative and body weight is stable, and so its time derivative is either 0 or very close to 0. If the average VO2 deviation is negative, then fat mass is persistently decreasing. For example, if the average VO2 deviation is negative 3.15 liters, then fat mass is persistently decreasing at about 1 kilogram per year. In addition, note that fat mass is also stable, since the body weight derivative is 0 or very close to 0. Therefore, under type 1 energy balance, fat mass is at the same time stable and persistently decreasing, which is clearly an impossible conclusion. Hence, all type 1 energy balance cases cannot exist. In Lecture 4, it was proved that, according to the calories in, calories out theory, at energy balance, the average daily net protein oxidation is dependent on the average absorbed protein intake and the average VO2 deviation. It was also shown that the protein balance is dependent on the average absorbed protein intake, the average net protein oxidation, and the obligatory protein loss. Now, in all type 2 energy balance cases, the average VO2 deviation is 0, and hence all absorbed protein is being oxidized. Thus, total body protein is persistently decreasing since the dietary protein is unable to correct for the obligatory protein loss, which implies that body weight is persistently decreasing. Yet, body weight is at the same time stable since all type 2 energy balance cases satisfy the energy balance hypothesis. Therefore, in all type 2 energy balance cases, body weight is at the same time stable and decreasing, which is clearly an impossible conclusion. Hence, all type 2 energy balance cases cannot exist. Again, in lecture 2, it was demonstrated that during prolonged weight stability, fat mass remains stable, while in lecture 4, it was proved that at energy balance, the average daily fat mass change is directly proportional to the average VO2 deviation. Next, observe that in all cases of type 3 energy balance, the average VO2 deviation is positive and body weight is stable, and so its time derivative is either 0 or very close to 0. If the average VO2 deviation is positive, then fat mass is persistently increasing. For example, if the average VO2 deviation is 3.15 liters, then fat mass is persistently increasing at about 1 kilogram per year. However, since body weight is stable, fat mass is also stable. Therefore, in type 3 energy balance, fat mass is at the same time stable and persistently increasing, which is clearly an impossible conclusion. Hence, all type 3 energy balance cases cannot exist. The previous discussion demonstrated that the enforcement of numerical consistency to all the cases that satisfy the energy balance hypothesis led to impossible conclusions. This was achieved through the application of the analytical results obtained in lectures 2 and 4, where all the results in the latter emerged from the axioms of the energy balance framework. Therefore, this proves that the calories in, calories out theory is a false paradigm, and as such, it must be rejected. To further substantiate this important finding, I now present a direct argument based again on the results of lectures 2 and 4 that illustrates that the calories in, calories out theory does not allow for normal physiology. Suppose that over many years, the average energy expenditure, the calories out, equals the average absorbed energy intake, the calories in. According to the calories in, calories out theory, this implies a state of prolonged weight stability. Thus, fat mass must be stable, which is equivalent to say that the average fat mass change is 0 over those years. Hence, the average VO2 deviation must be 0, implying that all the absorbed macronutrient mass is being completely oxidized as shown. Such result is, however, inconsistent with normal physiology, since it implies that the cellular synthesis of life-sustaining molecules derived from fat, like phospholipids, carbohydrates, like nucleotides, and protein, like myosin, is no longer possible, as all the diet-provided building materials are being oxidized. Therefore, the calories in, calories out theory does not allow for normal physiology, which provides more evidence on the internal inconsistencies that afflict this widely accepted framework. I now provide a qualitative interpretation of the previous argument that demonstrates, without equations, that the energy balance hypothesis has an implicit flaw that has remained unnoticed by the nutrition and obesity science community. The energy balance hypothesis asserts that if the difference between the average absorbed energy intake and the average expended energy is 0 or insignificant, then body weight must remain stable. This signifies that there is no energy accumulation, which in turn indicates that all the absorbed nutritional energy is being expended. This can only occur if all the absorbed macronutrient molecules are being oxidized to produce energy, and none are left to maintain and repair the structural constituents of the body. Thus, if the calories in, calories out theory is in effect true, then the only purpose of absorbed macronutrients is to serve as energy fuel, which is evidently impossible. Therefore, the calories in, calories out theory must be a false paradigm by reduction to the impossible. By using the method of reduction to the absurd or the impossible, we have confirmed that the energy balance hypothesis of the calories in, calories out theory leads to impossible conclusions, which signifies that its negation must be true. In other words, it must be true that at a steady weight, the average absorbed energy intake is significantly different to the average expended energy. Hence, the calories in, calories out theory is a false paradigm. This conclusion is likely to at least raise two concerns in those who subscribe to the calories in, calories out theory. The first is discussed in this slide, while the second in the next slide. The first concern is that such conclusion represents a violation to the first law of thermodynamics. In Lecture 3, however, it was shown that the coincidence of energy imbalance with a stable mass is not a violation of the first law of thermodynamics. Hence, this concern is invalid and simply denotes a lack of understanding of this physical principle. The second concern is as follows. Experimental evidence shows that a negative energy balance correlates with weight loss, whereas a positive energy balance correlates with weight gain. How I explain these findings if the calories in, calories out theory is indeed a false paradigm? As exemplified by Aristotle's theory of motion, we saw that it's possible to collect experimental evidence that is in perfect agreement with an erroneous theory. Thus, in the same way that the simultaneous drop of a feather and a stone seems to validate the false hypothesis that heavier objects fall faster than light objects, it is also possible to design experiments where a negative energy balance is associated with weight loss, whereas a positive energy balance is associated with weight gain. Furthermore, in the next slide, I will show that body weight fluctuations are well described by a mass balance model. Therefore, energy imbalance does not always lead to weight change. When it does, it's because the given level of caloric imbalance occurs simultaneously to a state of mass imbalance, which means that the average daily mass intake is not equal to the daily average mass loss. In other words, the effect of a particular degree of energy imbalance on body weight is ultimately a consequence of its corresponding mass balance status. In 2020, I published in the journal Heligion a manuscript that shows that it's possible to model changes in weight and fat mass in terms of mass balance. On the surface, this choice may seem equivalent to the calories in, calories out model, since an energy density factor should convert one into the other. Nonetheless, as we will see, this is not the case. To demonstrate such point, I now present a computational experiment that compares the mass balance model versus the calories in, calories out model proposed by Kevin Hall and colleagues in 2011, which is the model behind the NIH Body Weight Planner. The simulation recreates the effects of changes in macronutrient composition when the calories in are clamped at weight preserving level. The numerical details of the simulation can be found in the appendix of my 2022 publication. In A1, during the first 150 days, body weight remained stable at 70 kilograms, while consuming 2,000 calories with 50% carbohydrate, 30% fat, and 20% protein. After day 150, the energy intake is kept at 2,000 calories, but the carbohydrate energy fraction drops to 10% and fat increases to 70%, while protein remains unchanged. Observe that the red curve, which is the calories in, calories out model, predicts that switching to a 2,000 calories low carbohydrate diet leads to a long-term weight loss of about 1 kilogram. The mass balance model, which is the black curve, predicts a long-term weight loss of around 5 kilograms. Figure A2 illustrates that during the first 30 days of the intervention, the calories in, calories out model foresees a weight loss of slightly above 1 kilogram, while the mass balance model predicts a drop slightly above 2 kilograms. Figure B1 illustrates the fat mass change that underlies the weight loss depicted in A1. Note that the calories in, calories out model predicts a long-term fat mass gain of about 0.3 kilograms, while the mass balance model forecasts a fat mass drop slightly higher than 2.5 kilograms. Figure B2 illustrates that during the first 30 days of the intervention, the calories in, calories out model anticipates a fat mass gain of slightly above 0.1 kilograms, while the mass balance model predicts a fat mass drop slightly above 1 kilogram. These computational results demonstrate that a mass balance model is not equivalent to the calories in, calories out model. Dietary interventions that approximate that described by the previous computational experiment has been executed by Kohn and colleagues in 2020. These researchers published a feeding study on 23 females with a mean age of 21 years that were weight stable for 4 weeks under a normal diet with 44% fat, 39.6% carbohydrate, and 15.4% protein, and then switch to a ketogenic diet of statistically similar energy content with 69% fat, 9.2% carbohydrate, and 21.9% protein for another 4 weeks, leading to a weight reduction of 2.9 kilograms and a 2% drop in body fat percentage. Results that agree with the mass balance picture of body weight fluctuations. Consequently, a mass balance model seems to provide a more consistent account of weight and fat mass changes in contrast to the standard calories in, calories out model. I now summarize the main conclusions of this final lecture. First, we have seen that the enforcement of numerical consistency to all the cases that satisfy the energy balance hypothesis led to impossible conclusions. Thus, the energy balance hypothesis is false, and so its negation must be true. That is, it must be true that at a steady weight, the average absorbed energy intake is significantly different to the average expended energy. This conclusion is supported by experimental data that show that in steady weight populations, the calories in are significantly different to the calories out. A consequence of the previous conclusion is that energy imbalance does not always lead to weight change. When it does, it's because the given level of caloric imbalance occurs simultaneously to a state of mass imbalance, which means that the average daily mass intake is not equal to the average daily mass loss. In other words, the effect of a particular degree of energy imbalance on body weight is ultimately a consequence of its corresponding mass balance status. And at last, the inconsistency of the calories in, calories out theory limits our ability to decipher the biology of body weight fluctuations, since by the principle of explosion, in such a framework, any hypothesis, either true or false, can be proven. To end this lecture, I would like to share a quote by Albert Szent-Györgyi, a Hungarian chemist that in 1937 won a Nobel Prize for his work on the isolation of vitamin C and for discovering the components and reactions of the citric acid cycle. In his book, Bioenergetics, he starts the part 2 of the tome with the following quote: "Research is to see what everybody has seen and to think what nobody has thought." Thanks for watching, and I hope you have found all the lectures very enlightening.